All right, my name is Michael Eiler. My presentation today is on hardware implementations and analysis of control systems, specifically with the ball balancing platform. So, briefly, the outline of this presentation is going to be a quick overview of the scope of my project and the path that I took to get there. I'll go over the basic system, and then I'll move on to the comparisons, and I'll address the different complexities and oddities that each of them included, and finally the results of my work. So first off, the project scope and the path. So the project objective that I chose was to I wanted to do something with hardware. I'm a mechanical engineering undergrad and I'm electrical engineering master's, and I really love that sort of in between the two. So in order for me to do this and to still meet the requirements of the class and also to kind of in um, to enlarge my horizons, my capabilities, I wanted to test multiple controllers on these or on this specific hardware system. So I picked three, basic PID just to sort of set a baseline. Uh, then I moved on to feedback linearization, which uh, we sort of touched on in undergrad controls, and um, maybe we mentioned it in linear controls. It's been a while, but we covered some new methods to make it a little more robust and to be a little more sure of ourselves. And finally, I wanted to go on to sliding mode control. So I'll review all of the steps I took to get there and go over the different results that I collected. Um, and finally, the project path. Um, so I don't know if you could see it very well in this last slide, and actually I think I'll talk about it a little more in the next one. But as you can see, it's thrown together, might be a little loose. It was sort of designed, but it definitely is made with not the most expensive parts, and that was sort of on purpose. I wanted to see if I could create a platform to test things on, and I wanted to kind of push the limits of how cheap I could go. Right, so the servos are the little plastic 9 gram servos, so they definitely are not the smoothest. The camera, I think maybe I was getting 30 frames per second, if that. Um, but this setup was pretty cheap, and I was pretty happy with it. Uh, However, I took it apart at the beginning of the semester after I built it 2 semesters ago, and so I kind of had to get it back together and get everything working again. So after I did that, like I said, I wanted to set a baseline, so I started with the PID controller, got that working fairly quickly. Had to work out some more bugs, converting to Python 2 to Python 3. But after I got that done, um, I moved on to more advanced nonlinear controllers. And the first step was to sort of make the right assumptions to get the equations in a form that I could work with. And finally, with a lot of prayer, a lot of patience, and a lot of head pounding, I was able to get some results. So, already kind of talked about this a little bit, but this is my basic hardware setup. I'm using this laptop as sort of the controller center, I guess. So it sends commands through serial to the Arduino, actuates the servos. The motion of the ball is captured by the camera using Python's OpenCV libraries, and that information is put back into the controller, forming our closed loop. Uh, this setup, like I said, it was in use last year. It took a little bit of tweaking to get it to work this year, but between the robotic vision class and a couple more semesters under my belt, it actually wasn't too bad, and it was kind of fun to revisit old hardware and to see design decisions I made then and how I would make those similar decisions now, and how those may have changed. By having this moving average, I was able to kind of smooth out the motion of the ping pong ball and was able to get better results because of that. So the first system, said this a million times, was a PID controller. Um, the other reason, besides just the fact that this kind of got my feet wet again in terms of integrating this with hardware, was I felt like it was a good way for me to show you what's possible and what to expect coming from this hardware. All right, so um, on to the linear feedback controller. But before we get there, I wanted to kind of go over some of those assumptions that I was talking about earlier. So here on the left, we have the original equations in motion for a ball balanced on a beam. If you took the undergrad controls class, this may or may not seem familiar. But Q1 is our position, Q2 is the velocity of the ball relative to some point on a line. Theta is the angle of the platform or the beam, I suppose, and theta dot is the velocity of that angle, or the angular velocity of the beam or platform. So in this format, it wasn't really put in a way that I at least felt comfortable using the methods that we learned in class. So I made two assumptions of varying broadness. The first one was pretty straightforward. It was the small angle approximation. So sine of theta, as long as you're in relatively small degrees, is comparable to theta itself. I looked it up. It was around like 14 degrees when it started to get iffy, and I actually have a saturation on my system at 9 degrees, so I knew I was never going to get close to that. So I figured that was a perfectly fine assumption to make. The other one, and this one, I feel like I can justify a little bit more because this is actually a discrete system, is the theta dot squared. So, like I said before, these are not expensive servos, and after doing some testing, I realized that they're actually running at a constant speed, or near constant speed, so long as they're actually adjusting to something. And so I said, well, what if we assume at each time step that that's some constant b? And making that assumption, although I admit it's a bit of a jump, was actually sort of foundational and allowed me to get these systems to work relatively quickly and comparable to a basic PID in much less time. So those assumptions being made, it reduced the equations of motion into this nice, straightforward, quote unquote, nonlinear function as we've seen in class before with our f and our g and our u. So with that being done, I was able to move on to feedback linearization. So at this point, I had to check if it's feedback linearizable. I looked at the system, calculated the row term. It was within the number of states. It was 2. So that actually made the transformation pretty straightforward. It actually happened to be the same as the original coordinates, which meant that it was also globally invariant, and a globally invariant bijection, I should say. That being made, or that assumption being made, I was able to put the equations into normal form, compute the gains, and move on to implementing it in hardware. So here we go. All right, I got to pick up the pace a little bit, but sliding mode control, for me at least personally, was by far the hardest of these to implement. That being said, once the equation was broken down into the form that we used in class, it was actually pretty straightforward. So we found a sliding mode. In my case, I chose s equals x1 plus x2. Found our a, h, and g terms, and was then able to compute our beta naught, our rho, and our beta x, or pick a beta x, I suppose. One interesting thing that I found was I actually had a negative g of x, and at first I was worried I wouldn't be able to use sliding mode control because of this, However, on second observation, I guess, I realized that I was able to um, set my u equal to a negative nu, and then proceed with that, and then put it back in terms of u at the very end. So that's the process I took. All right, so that pretty much wraps it up for my presentation. These are the different distributions in terms of the air. So based off of 0, where was the ping pong ball at any given time? And as you can see, the blue line, which represents our linear feedback, did fairly well. You could say all of these I can kind of stay grouped together. PID in the orange was the closest, in my opinion, to actual 0. And finally, sliding mode control actually had what I believe, looking at this data, is the only non-bimodal distribution. So I feel like it was a lot of fun doing this. I really enjoyed it. I hope you did as well, and I feel like this was a great semester. So thank you so much.